Yeah, very good morning to all of you. So, in the last two lectures, we tried to see how the machine number represented in a uh, in a in a computer machine, and also what type of uh, errors present there, such as rounding, chopping, and so on, and how you will get the uh, polynomial approximation for a given function f in terms of series expansion. And we have done a few examples based on type of stability issues. uh, so here now we are now starting with the main content of this course. And the first, we are going to see the nonlinear equation f of x equals to 0. So there are various situations where the equations may cannot be solved analytically, or solution is not possible. Exact solution is not possible, such as x is x minus 10x equals to 0. Um, Other example is e to the power x is equals to sine x, and so on. However, there are equations like which you are known, the quadratic equation, this ax square plus bx plus c is equals to 0. That is can be solved by direct method. It's like, okay, means you require a very few number of steps to solve this quadratic equation. In fact, you have a formula that the roots are x equals to minus b plus minus square root of b square minus 4ac by 2a. 4ac by 2a. So similarly, if you have the cubic equation, uh, if you have the cubic equation ax cube plus let's say here, okay, so let's uh, erase this here. If you have a cubic equation, with the real coefficients, then it has at least one real root, because fundamental theorem of algebra always tells that the polynomial of degree n with real coefficient has always exactly n roots. And further, if you relate that whenever the complex roots occurs, so the roots may be real, all may be real, or maybe some of them are complex number, or some of them are rational. Yeah. uh, what then complex numbers always occurs in conjugate pairs. So if a plus ib is a root, then a minus ib is also a root. So for the cubic equation, it has at least, that implies that has exactly three roots. So at least one of them is real, other two may be complex conjugate to each other, or other two may be reals. Other known method for solving biquadratic equations are Ferrari's method, and so on. So some direct methods are also available for some specific type of equations. Uh, okay. Now, so as I told, there are situations where you may not able to find the exact solution. So for example, you have the application like a diffraction of light, where this x minus this equation is given by x minus 10x equals to 0. And another which you cannot solve directly, right? Okay, so you certainly require here a numerical scheme for finding the roots of this equation. Similarly for Kepler's equation. Similarly for Kepler's equation. So here sine function is involved. This is nonlinear equation. Whenever you have transcendental function involved, okay, so or a trigonometric function involved, this is a nonlinear equation, right? So this also cannot be solved analytically. So how to solve them? So that is our aim. Now whenever you have the equation f of x equals to uh, 0 and we are seeking the roots, means like we are seeking in r such that f of r is such that f of r is such that f of r is equals to 0, right? So now what we are interested in, how many time it becomes a root. And suppose you know r is a root, how many times? So we need to decide multiplicity. Okay, so once you tell that it's a one time, so definitely x minus r will be a factor of means will properly divide this function, and you will have some, it's some g of x if it is a one time. If it is a two time, it again this also can be divided when x minus r and so on. So if r is two time roots, you will always able to write f of x is equals to x minus r whole square times g of x, where g of r is non-zero. G of r is non-zero, right? So how to decide the multiplicity of the root? So this is what the first definition which states that root of multiple, how to decide the a root given number is a root with multiplicity m of a real or complex valued function f, as just now specified, that if you can write f of x as equals to x minus r to the power m times qx, with the proper where qx should not tends to 0 as x tends to r. Okay, not only q of r is 0, so not means but also the left hand limit and right hand limit must also not be 0, right? Okay, so means this will decide, if based on this you can decide what will be the multiplicity of the root r. It's not that easy always to deal with this definition so easily. It looks mathematically fine. Okay, so we will have also equivalent definition in terms of derivative as well. Okay, so that we are going to also learn further. So let's first discuss to find this problem, find all the roots and their multiplicity of the equation. So this equation, if you carefully see here, x equals to 1 is a root. X equals to 1 is a root of this equation. So if you replace x by 1, so 1 plus 1 minus 12 plus 2 plus 41 minus 51 plus 18. If you see x equals to 1 will satisfy. But how many times? So you can use synthetic division to see what will be the remainder and so on. Okay, so let me uh, go with it. Okay, so you have, if you want to use the synthetic division, I'm going to divide 1. Okay, 1 1 minus 12 to 41, minus 12 to 41 minus 51 18, minus 51 18. So we are going to divide it by factors, so you are going to use, this is a synthetic division, so I'm use this is 1 1 2, we are multiplying here by this 2, this is minus 10 minus 10, this is minus 8 minus 8, this is 32, 32 times 1 is 32, so that is minus 18. Now this is minus 18 times 1 is this, so this will be the remainder. Now if you see it again carefully, so this is the coefficient of x power the reduced by 1. So this is, earlier is a 6-degree polynomial, say 5 x power 5 coefficient, this is x power 4, this is x power 3, this x square, then x, and then constant term. So again if you look at carefully, this again 1 becomes the root by inspection. So 1 into 1 is this 3 minus 7 minus 15 minus 15 is this is something I have done wrongly, that 1 this is 1 into 1 is 1 plus 1 is 2, this is 2, minus 12 plus 2 is minus 10, this is minus 10, minus 8, and this is 41 minus 8 is, this is 33, this is 33, and this is here 33. Okay, let me let me rub this. Okay, right. So if you see here, this is a 33, this is 33. Now it's fine. So now this is all, this is fine. So 3, this is minus 7, minus 15, this is 18, this is 18, this is 0. So this is the coefficient of x cube now, x power 2, x power 1, sorry, this is x fifth, so x fourth, so x power 4, x this is coefficient, the first is the coefficient of x power 4 now reduced by 2. Now again if you see that this 15 plus 7 is minus 22, 18 plus 3 plus 1 is 22. So again this 1 becomes a root, so you have this is 1, 4 minus 3 minus 18, this is 0. So you have this now x cube plus 4x square minus 3x minus 18. So this is the root. Now if you look at carefully, this is so what is this? So x equals to 1 is repeating 3 times. So 1 comma 1 comma 1. Now the remainder is x cube plus 4x square minus 3x minus 18. So we are seeking for another x values. So if you look at x equals to 2, x equals to 2, then you have this is 8 plus 22, 4 into 4 is 16 minus 6 minus 18, so it becomes x equal to 2 is a root. So yeah, so here you again to use synthetic division. So this is 2, 6, this is 12, this is 9, 18, this is 0. So what is remainder is, so you have one more root is 2. Similar, now what is the remainder is x square plus 6x plus 9 equals to 0. This is x plus 3 whole square, so minus 3 minus 3. So you have all the 6 roots here. So one has the root of multiplicity, one is has the multiplicity 3, 2 has multiplicity 1, simple root, and the minus 3 is a root with multiplicity 2. So this is how you will follow with the this problem, right? Okay. What about the next? There another problem is show that the 0 is a root of the following equation. 0 is the root of this equation. with multiplicity 3. So if x equals to 0, this 2 into 0 is 0, and log of 1 minus 0 by 1 plus 0 is 1. So you know log 1 is 0, ln1 is 0. So 0 plus 0 is 0. So x equal to 0, one time root is clear. Now what about other? How? So you are going to, so you can rewrite. Now you're going to use the fact that log of 1 minus x is equals to, or 1 plus x is equals to x minus x square by 2. You can use this 2 plus x cube by 3 minus x power 4 by 4 plus and so on. So similarly you can replace x by minus x. For this you will get this, and 2x will get cancelled, and you will only start with this x cube. So you have okay. So similarly log of 1 minus x, so you can write this equation. This equation implies 2x plus log of 1 minus x. Log of m by n is log m minus log n, minus log of 1 plus x is equals to 0. So now use the fact that log 1 plus x is this. Log 1 minus x can be obtained by replace x by minus x. So once you do that, 2x will get cancelled, and you have minus x square by 2 will get cancelled with here, because here minus x square by 2 with plus sign, and minus minus here plus. So minus x square by 2 will get cancelled. Only you remain with 2 time of this something. You will get starting the polynomial with x cube and so on. So this 2x will get rid of, and the square term will also get rid of. We are starting with cubic degree polynomial, so that you can simplify and see that you can write this actually. This one you can write the left side of this. You can write that x cube time some g of x, where g of x is not tending to 0 as x tends to 0. So that where this limit x tends to 0, g of x is non-zero. That you can verify very clearly, okay, by just simplifying, and you can see that. Okay, fine. Okay, so another equivalent result of, or you can say another equivalent definition for deciding the multiplicity of the root for a given equation f of x equal to 0 is, can also be established by using this result here. Okay, so which uses that fact that f is differentiable function with m means m times. So you are saying a root with multiplicity m means you require the differentiability of function f m times. Okay, so how, see, so when you will say that the equation f of x equals to 0 has a root of multiplicity m at x equals to c, if and only if. So you have f of c 0, its first derivative 0, second derivative 0, and so on up to m minus 1th derivative is also 0, but mth derivative is non-zero at that point. So, and you are assuming that that mth derivative is here continuous. Okay, so you don't require limit m x tends to c f of mx is non-zero. Because of the continuity you can directly write, because they are equal, you know, limit x tends to, okay, you know, if mth derivative is continuous, then you no need to write in the limiting way. Okay, so means I can replace this limit x tends to c f mth derivative of x is non-zero. I can replace this by f mth derivative at c itself. This is f mth derivative of x, not mod here. So this is how you can also define the multiplicity of root. Okay, right. Yeah, so for an example, you can discuss the multiplicity of the root 0 for the equation sin x equals to 0. So, this sin x function is, you can differentiate as many time you wish. Now, this is f of x is equals to sin x. So, f of 0 is 0. So, it's a one time root at least, we know. So what about its derivative? So if you see what is the derivative of f is here is, what is the derivative is f derivative of x at x is equals to cos x, and cos 0 is, and cos 0 is 1. Now so f dash of 0 is equals to 1, which is non-zero. So by above result, we can say that this is a simple root, or it's a with multiplicity 1, right? Okay. So the available root finding methods are, means some of the methods are direct methods, means they will give you the exact solution. For example, quadratic equation, as we discussed at the starting phase. Other methods are, the second approach is iterative methods, means it will means you are slowly approaching towards the solution by following some numerical technique. The third is also a iteration method, but it has a specific name, fixed point. Okay, so that we are going to see why it is called fixed point iteration method whenever we are going to discuss the same thing. Okay, so as we discussed that the direct methods, I told it produces solution in a finite number of steps. So for example, find the roots of the quadratic equation. So this is very simple. By just substituting the formula, is a one step problem. Similarly, for the cubic equation, if you somehow by intuition you can find the real root of that equation, one real root, other can be found in the other way. By just using synthetic division, you can find the remainder, which will be a quadratic equation, and you can solve it, find another two roots of that equation. For biquadratic equation, you can use Ferrari's method, and so on. So there are some direct methods are available, but they are only only for very specific problems, not for, you cannot generalize for all type of problems. So if, okay, right, okay. So we are moving towards to see this iterative methods or enclosure methods. So as a statement says that these all are based on intermediate value theorem. So during the calculus, you must have uh, 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 must have been told that intermediate value theorem is a very important tool for deriving the numerical schemes. So what it relates, it is related with the continuous function. So if a function is continuous, then it assumes all of its values at every point of the interval. Okay, means you have, if I want to explain by a graph, you have function f. So this is, let's say here, this is a here, and let's say this is b. So this is f of a, this is here f of b, and this is f of x curve. Okay, so you take any point here, let's say this is k, it lies between f of a and f of b. You will always able to find a point c such that this f is equals to f of c is equals to k. Okay, means it has image. Okay, that whose image is k, right? So this is what this intermediate value theorem state, that let f from this closed interval is very much required. So let f from a closed ab be continuous, and let k is any real number that lies between f of a and f of b. Then you always able to find a c such that f of c is k. So okay, what is the very next result? is called Bolzano's theorem. Okay, so what it says is, let f is a continuous function of this again defined on the closed interval a to b. Be a continuous function. It's a very important thing. And let's say you have decided this, so this you can feed what are these a and b, so that this f of a into f of b is less than 0. Or what we can say, f of a and f of b are of opposite signs, means either f of a is greater than 0 and or f of b is and f of b is less than 0, or means they are of opposite sign, they will not share the same sign. Then you will always have, then intermediate value theorem always tells you that f of x has at least one root or an odd number of roots in a. So if you have this here and you have the graph, so f of, suppose the graph is like this, so f of a is here and this is f of b. Okay, so it will always, when it is continuous and you have the situation like f of either f of a lies below f of b or above f of b. Okay, but it will always intersect the x-axis, that's what the aim. Okay, so Bolzano's theorem is an application of an intermediate value theorem. So because 0 is also lies on the curve, so you'll always able to find, you can always locate an r such that f of r is 0 by intermediate value theorem. So this is not only the situation, so f of a and f of b like this here, so then f of x has at least one root, this actually guarantees at least one root, not a u. Okay, or an odd number of roots in a or b. Okay, so there may be situations means like you have like this, you are having curve, so you will have one root here, then another root here. Okay, this is intersecting 1, this is 2, this is 3, so 3 roots, odd number of roots. So if you're again one more graph is here, so you have okay, let me make it more clear. Okay, yeah, so if I have the graph like you have let's say your f of a is starting with this, then it's suddenly coming down, and you are having this here coming down, and so on. So this is your f of a, this is your f of b, so here is f of a, this is f of b. So how many roots you can see in the locating? So you will see odd number of, this is 1, this is 2, this is 3, this is 4, and this is 5. So the Bolzano's theorem gives you at least one root or an odd number of roots in open interval AB. Okay, so right, so determine so let's see this problem here. Determine intervals in which the roots of the following equations lie. Yeah, so by looking at the equation you can judge that so if I say the left side is f of x, means in the first problem I'm talking about, so let's, this is f of x is equals to x cube plus 2x square minus 3x minus 1. So now if you see f of 0, what is f of 0 is minus 1, which is less than 0. Okay, what about f of 1? If I have f of 1, this will be also negative. Okay, what about f of 2? So if I see f of 1 is also less than 0. Similarly, if I say f of 2, what is f of 2? So what is f of 2? Is equals to 2 cube is 8, plus 8 is 16, minus 6 is 10 minus 1. So f of 2 can be seen as greater than 0. So the root will be lie in the interval 1 comma 2. if I see f of 1 is negative and f of 2 is greater than 0, it's a polynomial. It's a polynomial. So polynomial is always a nice function. You can differentiate as any time. You can this is function is infinitely differentiable. It's continuous everywhere and so on. Okay, so Bolzano's theorem conditions are satisfied. So you have a equals to 1 and b equals to 2. It has at least one root there. That's a guarantee from there. So it determine intervals. So it maybe you can decide 0 comma 2 because f of 0 is negative and then f of 2 is positive. That's also fine. Okay, similarly for the second case. For the second case here, you can see f of 0. So if you replace x equals to 0 here, see this if you see in the second case, okay, in the second case you have to use the calculator for this. Okay, uh, you have in the second problem f of x is equals to 3x minus cos x minus 1 minus 1. So if you see f of 0, that is 0, this is minus 2 minus 1 minus 1 minus 2, which is less than 0. Okay, what about f of pi? That is equals to 3 times pi minus cos pi. So cos pi is minus 1, so minus minus plus, so plus 1 minus 1, so that is p pi, that is greater than 0. So the interval is 0 to pi, I guess, by using Bolzano's theorem. Again, this is a function. This is a function. One sum of this is 3x is a polynomial. 3x minus 1 is a polynomial and cosine function. So sum of two continuous function is continuous, and this is a very nice function again. So all the conditions of Bolzano's theorem satisfied, and the interval is corresponding interval is 0 to pi, where at least one root will be there. Right. Okay. Okay, so let's learn the bisection method now. So that also known as method of interval halving. Means every time, what does that mean is every time you are going to make the length of the interval is divided by 2. Okay, so you will understand by looking at the process more clearly. So here in bisection method, you have to apply the Bolzano's theorem repeatedly. That's a very important thing here. Means again and again you have to identify a and b such that f of a into f of b is less than 0. Okay, right. Okay, so what is these are the steps. So first you have to, so you are supposed to solve an equation f of x is equals to 0. You want to identify r such that f of r is 0, but exact root may or may not be achieved. You need to achieve an approximation, good approximation. So suppose f is continuous, and you can decide a and b such that f is continuous, and you can decide a and b such that f of a into f of b is less than 0, means they are of opposite sign. Okay, this is they are of opposite sign. Okay, they are of opposite sign. Okay, so let's call them a1 and b1. Then you take the midpoint of that interval. So I have, so here what is there is happening is you have decided this is a1 and this is b1 such that f of a1 into f of b1 is negative. Then you take the midpoint of the interval. Let's call x1, that's a1 plus b1 by 2. So I can write this as a1 plus b1 minus a1 by 2. That's for analysis point of view. Okay, now you check the sign of f at x1. Okay, and then you check the product with f of x1 into f of a1 and f of x1 into f of b1. Okay, So either one of them is negative, then you will proceed with the same. Okay, so if f of a1 into f of x1 is negative, so root lies here. If f of a1 into f of x1 is negative, then root lies here. If f of x1 into f of b1 is negative, then the root lies here. Means you are going to leave, in this case, suppose first case, if f of x1 into f of a1 is negative, means your root lies here, so you are going to discard this interval, discard this part, and you are start working on this. Okay, and repeat the process now. Then again you subdivide. If it is not the exact root, you will get another root, and then you will repeat the process here. Okay, right. So let's go further now. So I can write this ax1 is a1 plus b1 by 2. This is midpoint of the interval a1 to b1. That's going to be rewritten as the following. So if f of x1 is non-zero, so if you have good luck, means like if you are very fortunate, you can directly find, sometime you may able to find directly the root, but it's not always the case. So means you will either f of x1 is greater than 0 or f of x1 is less than 0. Then as I mentioned, that you have to see whether f of x1 into f of a1 are of opposite sign, or f of x1 and f of b1 are of opposite sign. So if f of x1 and f of a1 are opposite sign, then the root lies between there, and then you will set. So what you will hear is, then in this case what you will do is, you have a1 to x1, because x1 is lies on the left of the a1, on the right of the a1. Okay, so what you will do is a2 equals to a1 and b2 equals to x1. That's what you are going to, means we are going to specifying the interval, so that we will get into some process, and we can easily write some code for this. Okay, right. So we set a2 equals to a1 and b2 equals to x1. Then again you divide the interval, means you take the midpoint of the interval a1 to x1, that's called x2, which can be rewritten as a2 plus b2 minus a2 by a2. So in this case, this is there. If f of x1 and f of b1 is less than 0, then the root lies between x1 and b1. So in this case here, so then in this case you will say this is a1, this is a2, and this is b2. Okay, and then you will say x2 is equals to a2 plus b2 by 2. Okay, so we set a2 equals to x1 and b2 equals to b1 and define this. Then you finally repeat step 1 and step 2 in the same fashion. Okay, so here this is how, then again you repeat the step 1 and step 2 in the same fashion to get the root. So you see, in this process we are dividing interval by means we are subdividing the interval with each time of length half, means multiplying by half. Okay, right. So how much we should go further, means how much step we should go. So there should be there must be some stopping criteria for this process. Okay, so there are that's so if you follow the step 3, keep on following. So if suppose you find xn plus 1 is very much clear to very much closer to x at the previous value, then you can stop either in this way, or in maybe means, or you can say that absolute error is up to some less than epsilon, maybe 10 to the power minus 4 or 10 to the power minus 5, and so on. Or you can look at relative error. So mod xn plus 1 minus another stopping criteria, it also can be possible. Okay, that instead of working with absolute error, you can also work with relative error to go for more accuracy. Other stopping criteria is because at each step at each step you are trying to, so this is your, you can say, first stopping criteria, this is your second stopping criteria, then again third stopping criteria. What I want to suggest is you are going to always check the sign of f of xn. Okay, so if this magnitude is less than epsilon, means f of xn may not be exactly 0, but is maybe absolute sense it's very closer to 0, that also can be stopped. And another stopping criteria is that final one, you can fix the number of iterations. Okay, you can fix the number of iterations, means you can only go for like 100 steps at the most, fixed number of iterations. That also one of the stopping criteria for doing the same. So this is what I did explain just now. Specify the number of iterations. That also one way the stop the method by adopting any of the criteria below. Okay. So let's have here two examples. So find roots of the following equations using bisection method. So the first problem here is x minus 1 to the power 7 equals to 0. So it's very clear this f of x is here is x minus 1 to the power 7. Now if you see f of 0 is negative, right? F of 0 is minus 1 to the power 7, and f of 2 is 2 minus 1 to the power 7, that 1 to the power, that is 1 is greater than 0. So root lies between 0 and 2. Okay, so and this function is a polynomial of degree 7. Okay, this function f of x is a polynomial. So this is a very nice function, it's a very continuous function, and you have found a equals to 0 and b equals to 2, where you can apply the Bolzano's theorem. So the Bolzano's theorem tells that there must be a root in between them. So if you apply the bisection method, means you are going to see the midpoint of the interval. So 0 plus 2 by 2, 0 plus 2 by 2, so that is equals to 1. And if you try to check the sign of f of x1, what about f of x1, that is f of 1, means that is f of 1 equals to 0, means you have got the exact root in a one step by using bisection method. If you choose carefully, a equals to 0 and b equals to 2. Okay, so in the second problem you have e to the power x equals to sine x, so closest to 0, we are trying to find the identify the solution closest to 0 for this problem. Okay, so let's we are trying to solve this equation e to the power x minus sine x is equals to 0, so that we will call as f of x. Now if you see f of 0 is 1, and that is always greater than 0. Okay, now what about e power x is always non-negative number, so whatever the x value you will take. Okay, so what other value you can take, but we are need to be close to 0. Okay, closest to 0. So if you see f of 1 means e minus sine 1. Okay, so if you try to use the calculator, okay, if you try to use calculator, that will give you that will give you at this is going to be approximately sub 2 sorry not 2 1.8768 something approximately. Suppose if you are trying to find f of 2 as then e square minus sine 2. Okay, uh, uh, e minus sine 2. Okay, yeah. Uh-huh. Okay, so what value you can choose so that e to the power x minus sine x is becomes negative. Okay, that's we try to choose now. If mhm. Okay, if you choose a f x equals to 3, still you will get the positive sign. Okay, and yeah. Okay, so if you mm, instead of pi by, yeah, so you need to see uh, uh, where you will get this. So we need to check the values of x such that e power x minus sine x is less than 0, means e to the power x is less than sine x. So that you need to carefully choose and apply the bisection method for the same. Okay, so I will try to provide the solution in the next lecture for this, right? Okay, the very important thing about iterative method is uh, that when you start doing start working with the iterative scheme, it actually generates a sequence of numbers, and what is the desired thing is that should converge to your exact solution. Then you will say this is a means your that your method is good, acceptable, and sometime it is also related with the stability thing. Okay, so it should that the generating a sequence of numbers should not be diverse, means it should not go away from the solution. So this is how you will so here is the definition of order of convergence. So how much and how much rapid it is, so how much faster it is converging towards the exact solution, that is what the definition will tell you. So this is x, so let xn is a sequence of numbers which is generated by some iterative scheme and converging to the exact solution c. So means you are priorly known that this is there, this already there. Okay, with each xn may or may not be equals to c. So if it is equals to c, you are achieved. Okay, so if you are every time xn is differs from c. So if there exists a finite non-zero constant m and a real number some p greater than 0 such that this limit exists and equals to m. Okay, then this m is called asymptotic error constant, and this p is called the order of convergence for the given method. So this p is called the order of convergence for the given method. Okay, right, fine. So we are going to now see the order of convergence for bisection method, how this method rapidly converges towards C. First we should confirm that whether it always converges Okay, that also a very good question here. Okay, or it may fail at some stage. So okay, based on the order of convergence, let us explain with some two examples. So this xn equals to 1 by n is a very familiar sequence which tends to 0 as n tends to infinity. And if you look at xn plus 1, so limiting, so c value is 0. If I go back, so xn plus 1 minus 0 divide by mod of xn minus 0, so that is equals to n plus 1 by n, and that will tends to 1 as n tends to infinity. So here asymptotic error constant is 1 and a p value is 1. For this case, p value is 1, so order of convergence is 1 and asymptotic error constant is 1. Okay, so for the next case, let's say x naught equals to 1 by 3 and xn plus 1 equals to xn square. So if you carefully look at this sequence, every time it means x1, what is x1 is x naught square, so that is 1 by 3 square. What is x2 is x1 square, means 1 by 3 to the power 4, and so on. And so it's a geometric series with common ratio r less than 1. Okay, and it will converge to 0. That's very clear. The sequence will converge to 0 as n tends to infinity. Moreover, you have so c value is 0 here, mod of, so therefore, so here mod of xn plus 1 minus 0 divided by mod of xn square is equals to 1. As n tends to infinity, this still remains 1. Okay, so the p equals to 2 for this case and m is equals to 1. So this is how you will decide the order of convergence for the given problem. Okay, so yeah, so we will look at this the convergence result for bisection method in the next session of the this course. Okay, it's another, the next lecture you will we will start from here. Right, thank you.